A very good morning to all of you. This is your 10th lecture. This is your lecture number 10 for the subject Power System and 1. So we had started in the previous lectures the concept of constants of a transmission line. So there are three constants of a transmission line named as resistance, inductance and capacitance. So there are three constants of a transmission line. So all these three constants we had started discussing in detail. So for the electrical design analysis, we have to understand the idea behind this constant to a great level. So we had started with the concept of resistance. We had discussed the formulas there, how to calculate resistance. Now we are going to study the concept of inductance. So the concept of while discussing the concept of inductance, we have to calculate the flux linkages, how to find the flux linkages, because all these parameters named resistance, inductance, capacitance are used to measure the voltage regulation as well as efficiency of the transmission line. Okay. By the knowledge of these parameters, we can easily calculate the voltage regulation as well as efficiency of a transmission line. So the basic formula for inductance is the rate of change of flux linkage with respect to current. So if we have to determine the value of inductance, we have to know the value of flux linkage and current. The value of current is already calculated, so we have to determine the value of flux. So how to calculate the value of flux linkage, we are going to learn in this video. So the inductance of a circuit is defined as the flux linkages per unit current, flux linkage per unit current. Therefore, in order to find the inductance of a circuit, the determination of flux linkage is of primary importance. So another thing is flux linkages due to a single current carrying conductor. ठीक है, तो हमारा क्या रहता है, हमारा फ्लक्स लिंकेजेस क्या रहेगा ड्यू टू अ सिंगल करंट कैरिंग कंडक्टर. So this is the example of a single flux linkages due to a single current carrying conductor. So this is a current carrying conductor. The current value of current I is flowing to the core of this conductor, and this is the resistance of the conductor. So this area is magnified, is shown in figure number 2. So here we can see that resist from the center to the surface, this is the radius of the conductor, and this is a point x inside the conductor, and the rate of change of this displacement is known as dx. Okay. So we have to derive how to calculate flux linkage due to a single current carrying conductor. So for this, so consider a long straight cylindrical conductor of a radius r meters carrying a current I amperes as shown in figure 1. The current will set up magnetic field. The magnetic lines of force will exist inside the conductor as well as outside the conductor. Both these fluxes will contribute to the inductance of the conductor. So flux linkages due to the internal flux, we are starting with the derivation part. So referring to figure 1 second part, which is magnified, where the cross section of the conductor is shown magnified for clarity. The magnetic field intensity at a point x meters from the center is given by magnetic field intensity is how much current is flowing through that particular part at point x and what is the circumference of the point x. So assuming a uniform current density, we have to calculate the Ix. So that is the current flowing throughout the overall conductor per unit area. So area of the circumference, area of that point. So the value is x square divided by r square into I. Pi cancel out. Again, when we go further, the value of hx, we have to substitute the value of ix here. The answer will be this. If mu equals to mu naught mu r is the permeability of the conductor, then flux density at the considered point is given by mu naught mu r hx Weber per meter square. Mu naught mu r x divided by 2 pi r square I. This is where the value of mu r relative permeability equals to 1 for non-magnetic material. Now flux through a cylindrical shell of radius thickness dx. Okay. Up now the rate of change of flux through a cylindrical shell of radial thickness dx and axial length 1 meter is given by this formula. Is given by this formula. Rate of change of flux linkage is flux density multiply I1 multiplied by dx. This is length in meter. So by substituting the value of magnetic flux density, we can determine the rate of change of flux in this form. The flux links with current Ix only. The rate of change of flux links with current Ix only. Therefore, flux linkage per meter of length of the conductor is this multiplied by the rate of change of flux. This is the flux linkage. When we multiply all the uh, you have to substitute this value in here and the final result will be there. So we had calculated the flux linkage inside the conductor. So for the calculation of the total flux, we have to integrate this part. So total flux linkages from center up to the conductor is calculated by integrating the part from and the integration limits are taken as 0 to r. So by substituting all these values r and 0, we get mu naught I 85 Weber turns per meter length is the total flux linking with the conductor from center to the surface. Thank you guys. This is all regarding this derivation. Thank you guys.